This is Pat OB from the Purdue University campus in Hammond, Indiana. In this presentation, I provide a working example that both summarizes the key results of a simple linear regression problem and the use of Excel spreadsheet in performing the analysis. So here's our key two-variable model, the dependent variable y and the explanatory variable x. So here's the mini problem right here, which poses the question: is there a relationship between return on investment ROI and the firm's debt ratio, a key measure of financial leverage? So you can read the rest of this, and here's the data set. So this is a cross-sectional data of 24 firms showing their return on investments and their debt ratios. And with this, we're going to perform a regression. This is the result, but I'm going to go to the spreadsheet right away. All right, so here we have it, right, from top to down. And so to do this, we go to data analysis. If you don't have data analysis, you want to go to your file and go to options and add it in. Okay, so we scroll down here to regression and OK it. And for input Y range, we highlight from the label, all right, and work our way down right there. Click here for input X range while cursor is blinking here. Go to the top of the file, and our X is debt ratio. Click, hold, and drag it all the way down. There you go. And be sure to check labels right here so the computer knows the first row here contains labels. And for confidence interval, which really is your alpha, we can leave it right here, 95%. But if you want to change it to 90% for an alpha of 10%, or 99 for alpha of 1%, you can do that too. So I'm just going to leave it right there. All right. You don't even have to check this, to be honest. You can just, it's by default, it's 95%. Then click right here for outputs. After you've clicked here, then click in this open rectangular window right there. All right, your cursor has to be blinking here for you to now scroll down to a spot on the spreadsheet to post your results. So let's click right there, and then the cell address registers right here. Now, for good measure, I'm just going to check residuals because I want to inspect the residuals of the model. You can also check residual plot, but I'd rather plot it myself. So we're done. So let's click OK. And here's our output right here. And for better visual appeal, I'm going to highlight I'm going to go home and kick it up a notch, you know, say to like font size 18. Okay, so let's make this look good. So you can see it, highlight that, and shrink it down some, like so. And do the same down over here. All right, shrink it down. And let's make all these look good. All right. Okay, so when you get your regression outputs, the very first thing to check is your F statistic right there. All right, because you want to first off confirm that the relationship is statistically significant. If the regression is not statistically significant, then there's no point carrying on. So our F statistic is 4.82 approximately, and all we got to do is compare it to the critical value. But you don't really need to look up the critical value. You can simply look at the corresponding p-value. Not sure why Excel calls it significance F, as you can see up there. So I usually like to overtype it p-value. Right, like so. All right, that's your p-value right there. So the p-value, as you can see, testing at the 5% level tells us that the regression is statistically significant because this p-value is less than 5%. So that's one. The next important thing that you want to look at, therefore, would be the B1, the value of B1. This is it right here. All right, this is the value of B1. All right, so B1, which is the slope of the line, is a negative 0.26, which will seem to suggest that for every 1% increase in debt ratio, that return on equity, return on investment tends to go down by about 0.26%. Is this statistically significant? Well, for that, let's look at the t-statistic. That's the t-statistic right there. And to determine whether this t-statistic is significant, we want to compare it to the critical value. And if this value is greater than the critical value, then we reject the null hypothesis and conclude that this slope coefficient estimate is significant, but no need to do so. All right, let's just look at the corresponding p-value right there. All right, and our p-value again is less than 5%, and so sure enough, this slope coefficient is statistically significant. Before proceeding, remember, in a two-variable model, aka a simple linear regression, the f statistic, if it is significant, the t statistic for the slope would also be significant. I've explained that in another presentation, showing that the test of hypothesis is actually identical because we are testing for the significance of the slope coefficient. I'll return to that shortly again. All right, now the third thing that you want to look at is your R square. Your R square is a proportion of the total variation in Y that has been explained by the regression. According to this result, actually let me increase that side just a little bit. All right, I'm going to go to Format and choose Auto Column Width. So this is a all-important R square. R square again is a descriptive statistic. It is not a test of significance. So you cannot be looking at R square before you look at F and T. All right, this is a descriptive statistic and simply tells us the proportion of the total variation in Y that has been explained by the regression. And according to this result, it says that about 18% of the variation in Y, which is return on investment, is explained by the regression. Is that high or low? Well, beauty or ugliness for that matter is in the eyes of the beholder. All right, so you may conclude that this proportion, that the portion of the variation in Y that has been explained is not so high, even though you have a statistically significant relationship. Not all relationships may result in a high explanatory power. Now though, but that's as far as we can go with that. All right, you can't preposition, so to speak, your R squared to your F. Now, be aware that R squared in a two-variable model can be obtained in one of two ways. You could either look at your correlation coefficient, which is this guy up here. Excel calls it multiple R, not sure why, but this is your correlation coefficient, a value ranging from -1 to +1. And also, by the way, we know that this has got to be a negative value. Why? Well, because we know that the slope is negative. But Excel doesn't distinguish. It just throws out the number. It'd be nice if they had a little negative in front. You could choose to do so yourself and put a negative there. All right. Anytime the slope of a line is negative, the correlation coefficient must definitely be negative as well. So anyhow, a couple of ways that you can actually calculate this number. One is by squaring the correlation coefficient, because this is R square. So if you hit equal there and you click on this and you put the hat sign from your keyboard and then 2, that's going to give you the same thing. All right, so you can shrink it down. All right, so it can look a little better than just throwing out all the numbers. The other way is, remember, R square is the ratio of your sum of squares regression and your sum of squares total. This is it right here. All right, so it's going to give you the same thing. All right, so your sum of squares regression is the explained variation component of the total variation, and your sum of and your residual is error, the unexplained variation. All right, and that's about it as far as the basic interpretation of Excel output is concerned. Your measure of unexplained variation could either be sum of squares residual, mean square residual, and standard error of the estimate. Keep in mind, standard error of the estimate is the square root, SQRT, of mean square error. If you click this, in close parentheses, you'll get the same thing as over here. All right. So now let's go back to the presentation and wrap this up. So again, this is the output, and I've labeled the key results to draw your attention. All right. So now let's pose a few questions and problems and respond to them. This says define the prediction equation. This is our prediction equation. So the prediction equation contains the slope estimate, sorry, the intercept estimate and the slope estimate. All right, the all important coefficient of x, which is the slope, the estimate of the slope parameter. So with this prediction equation, if someone were to say, well, what will y be if x is, say for example, 10? So put 10 here, multiply it by your slope estimate, and then sum that up with this. In this case, our slope is negative. So as you can see, this negative has to appear right here. So whatever x is, you'd have to put it in here and then sum it up with this to find what y will be. This says give a 95% confidence interval for the slope. All right, for that, that's our definition right here. It's equal to the slope estimate plus or minus the margin of error. This whole term is margin of error. So the margin of error includes your t-statistic, which you find based on the degrees of freedom n minus k. In this case, n minus 2. So based on 22 degrees of freedom, all right, there are a total of 24 observations minus 2. Based on 22 degrees of freedom at the 5% level, which is 95% confidence, you find the t value to be 2.074. The standard error from the regression is part of the output. So if you go right here, go back here, this is our standard error, all right, for this coefficient, 0.1192. And that's what you see here. So crunch it all out. The lower limit is going to be a negative 0.51 approximately, and the upper limit would be a negative 0.014 approximately. Excel also gives you that as part of the output. So if you go back over here, you see it right here. All right, these are the confidence limits for the slope coefficient right there. All right. And then next up here says, now test the regression hypothesis. All right. You know, does debt ratio have a relationship with the return on investment? That's our statement of hypothesis. So in a two variable model, B1 is the measure of, is the indicator of that relationship. If B1 is 0, then there is no relationship because this is the coefficient of x, the explanatory variable. So according to our output, f is this value with a p-value of less than 5%. And therefore, we reject this null hypothesis, concluding that there is evidence that, in this case, a negative relationship exists between debt ratio and return on investment. In the same vein, we wish to test the slope null hypothesis. In other words, does debt ratio contribute information in the prediction of return on investment? Or alternatively stated, does debt ratio have an impact on ROI? All right. So right here, again, the statement of hypothesis is going to be identical to that of the regression. I go back to that of the regression hypothesis because the slope is the only parameter that is of essence here. Now for that, we look at the t and then the corresponding p-value, which the p-value will always be identical. The p-value for the t-statistic will always be identical. I go back here to the p-value of the f statistic in a two-variable model, even though these are two different statistics, f and t, but because it's a two-variable model, this indicator of the highest probability of type 1 error, the p-value, would always be the same. And so now, because this is less than 5%, we conclude that there is evidence that the slope of the regression line is not 0. And we can also conclude specifically with respect to this study that for every 1% increase in debt ratio, ROI tends to drop by about 0.26%. Then it says construct the residuals, and do the residuals appear random? So that's the result right here. And actually, the reason that I wanted the residual output is so I can plot them. The computer will give you y hat, which is the predicted value of y, as well as the residuals, which is our error right there. All right, so if you highlight these two columns, it's going to plot the residuals against y hat. That's what it's going to do. Keep in mind, when you have two columns of data on spreadsheet, the spreadsheet will look at the first column as your x and the second as your y in that logical order, x, y. So then when we go to insert and choose the scatter and choose the first one here, that's it. So it's plotting x. All right, sorry, it's plotting y. All right, x is your horizontal axis, y is your vertical axis. So it's plotting y, your residuals, which you see right here. So now going back over here, do these appear pretty random? I say they do. All right, so it looks pretty white noisy to me, and that's what we want them to be. We don't want to see any kind of systematic pattern in the residuals, because if we see something that appears to suggest some nice funky pattern, then it's telling us that there's information embedded in the residuals, in which case they cannot be said to be white noise, or as we say in econometrics, IID, identically and independently distributed about a mean of 0. So I'm happy with this, so we proceed to wrap this up. It says give a 95% confidence interval for the expected return on capital with 0 debt. So now let's see. This is the confidence, this is the prediction interval for the mean value of y. All right, so the prediction interval for the mean value of y is so defined, which is the predicted value of y hat plus or minus this margin of error. The margin of error is your t-statistic multiplied by the standard error. But first, let's get y hat. So for this problem, it says do that for a company with 0 debt, where x is 0. All right, so which fortunately is within the range of values we have for this study. In fact, there are 2 firms in our data set where x with 0 debt. So we can carry on with this because we want to make sure our prediction is within the sampled range of values for x. So for that, y hat, this is the definition of the prediction equation, remember? So plug in your b0, plug in your b1, and x is 0. So eventually this comes out to be the intercept. So the expected return on investment would be about 29.36% for firms with no debt. And so you plug that in here. That's your y hat plus or minus the margin of error. So put in all the values, substituting everything, and this comes out to be the lower limit is 23.05, the upper limit is 35.67. So it says we can say that we're 95% confident that on average the return on invested capital for a firm with 0 debt will range from 23.05% to 35.67%. So this one here is a point estimate, this y hat here, and this is the prediction interval right here within which the point estimates would lie also. Now Excel also gives it to us. All right, so if you go right here, all right, that's actually what you see at the top right here. All right, so for some reason Excel gives it to us twice. All right, both the prediction interval for b1 and the prediction interval for y hat. So it repeats it, and usually what I do when I get my output, I highlight these 2 columns and kill them. All right, so I have a more a simpler output showing. But that's all there is to it.